Everyone, welcome to all of you in my channel. So those who have not subscribed, please subscribe the channel because ultimately you'll be getting lots of benefits from this particular series, especially PYQ series. So continuously I'm putting lots of PYQ questions. I'm solving all of these questions and also explaining all these concepts over here. So in one video you'll be able to understand all of these previous year questions. So definitely it is going to help you a lot in your examination. So let's start with the problem first. So here you can see a pulse tracer is introduced in an ideal continuously stirred tank reactor. So you have a continuously stirred tank reactor here, and pulse tracer is being introduced at t equals to 0, and the mean residence time of this reactor is tau. The time taken to the exit concentration to reach means they are asking you to when CAT will be equals to CA naught by 2. So what is equals to time? So if inlet concentration is CA naught and this is the exit concentration at CAT. So if we talk about the CSTRs, a pulse tracer inputs output. So CAT concentration at the exit of the reactor at any time, that is equals to CA naught into e to the power minus t by tau. Right, so you are supposed to calculate time when CA equals to CA naught by 2. So we can write CA naught divided by 2, which is equals to CA naught into e to the power minus t by tau. It will get cancelled out. So you will see 1 upon 2, that is equals to e to the power minus t by tau. So if I'll take ln, so ln 2 minus ln 2, that is equals to minus t by tau. So minus will get cancelled out. So time will be equals to tau multiplied with ln 2. So that will be equals to 0.693 tau. So this will be your answer. So from here your option D will be your correct option. Okay, this was very simple question that is completely based on the formula. But now moving towards the next question. This question is also very important question. This question is basically based on graph only. So here you can see a step input tracer test is used to explore the flow pattern of fluid through a vessel of total volume equals to 1 meter cube having a feed rate of 1 meter cube per minute. So the total volume of vessel is given to you, that is your 1 meter cube, and again volumetric flow rate is also given 1 meter cube per minute. So curve first, if you will see here, so this curve looks like this way, and at the end this one is there and 20, and if this is C and this is time, and at a particular time 40 second the concentration is given 1 upon 1 by E multiplied 20. So when we see this curve, so this curve step looks like CT, that is equals to C naught into 1 minus e to the power minus t by tau. So this curve look like the output response or concentration of tracer at any particular time t while using the step input of CSTR only, right? So curve 1 indicates your CSTR. So if you see that curve 1 is your option A's option will be your 4. So A is your 4. Now moving towards the second one. Second curve shows like that. So this is the concentration and this is the time. So it is going like that. And again this time is 20, and at t equals to 60 second, this one is 20. Concentration is given 1 upon 1 by E into 12. This one is 12. So whenever we see this particular value, maximum value in step input, this is called C naught. And here this curve look like something like that, CT, that is equals to C naught. And when t is less than 20, so concentration is 0. So you can say this looks like in this way, CT equals to 0 when t is less than 20, and that is equals to C naught into 1 minus e to the power minus t minus tau p divided by tau m when t is greater than equals to 20. So this kind of curve indicates that when CSTR is connected with PFR, or when there is a PFR in series with the CSTR, something like that, right? So where tau p is the space time for the PFR and tau m is the space time for CSTR. So CSTR, this is PFR plus CSTR. So CSTR is connected with PFR, or PFR is connected with CSTR. So option B's answer will be A. So your option B is your correct answer, right? This thing. So this was also just a theoretical question, but again in theoretical questions also you need to understand what kind of formula that can be used. So later on in the same lecture we will see how you can solve the numerical on this particular concept also. It's very very important concept. The next question says that for a packed bed reactor, the presence of long tail in residence time distribution curve is an indication of. Okay, so whenever we talk about residence time distribution from a packed bed reactor, something like that. So in packed bed reactor, you will see. So the packing material will be looking like in this way. So if any reactant is entering in this reactor, something like that, so it will be coming out of the reactor. So due to this kind of packing, sometimes what will happen, the packing materials inside the reactor will get stuck in this particular zone, and this is going to form a dead zone kind of thing. And that's why you will see in exit distribution function. So in exit is concentration versus time. If I am plotting, so it will be looking like in this way, something like that. Okay, so you will see there is a long tail, and this long tail is occurring due to presence of your dead zone in your packed bed reactor. So option C will be the correct option here. Correct answer here. Okay, this was also a theoretical question, but again all of these questions are very very important. You should know the concept regarding that related to this particular problem. Now coming to this problem, this question is also very very important. This question has been asked in grade 2007. So in this particular problem they are telling a pulse of concentrated KCl solution is introduced as a tracer into the fluid entering a reactor vessel having a volume equals to 1 meter cube and a flow rate equals to 1 meter cube per minute. So the total volume that is equals to 1 meter cube and volumetric flow rate V0 is equals to 1 meter cube per minute. Is that clear? And the concentration of tracer measured in the fluid leaving the vessel is showing in the figure. So the concentration response of the concentration or this concentration curve is given to you, that is CT versus time. And if you'll see, this curve is starting from 20, so 20 will be your concentration CA0. So CA0 is equals to 20, or I am assuming C0 only, that's it. C0 is given 20, and now you can see the nature of the curve is like that, something like that, and this will go and decay like that, something like that. So this curve is concentration versus time, and at t equals to 50 second, you will see at t equals to 50 second, and this time is your 20. So the concentration has been given to you, and this concentration is called as 20 divided by E. So the numerical value of concentration has been given to you at t equals to 20 second. Okay, and now you are supposed to calculate here, since this these kind of models are there, but in these models you are supposed to understand what is the residence time and all of these things for this CSTR and PFR and dead zone also. So in this model they have given that the flow model parameters that fits in the measured RTD in terms of one or all of the following mixing elements, namely volume of PFR. So they are trying to tell you there is a model that works in this kind of problem. So there is a PFR, and obviously two different kind of reactors are there which is connected in series, and obviously in this reactor also there is dead zone, right? So if I am assuming volume of plug flow reactor is VB, volume of mixed flow reactor VM, and VD is the volume of dead volume, right? So if you see that what is C0, so C0 we have calculated, and whenever PFR is connected in CSTR, the concentration CT can be written as C0 into, and this is a pulse tracer experiment, C0 into e to the power minus T minus tau P divided by tau M. So CT is given to you 20 divided by E, that is equals to 20 multiplied with e to the power minus 50 minus tau P. Tau P is 20 obviously, and tau M we don't know, so tau M. So 20 and 20 will get cancelled out. So e to the power minus 1 equals to e to the power minus 30 divided by tau M. So if you will calculate this thing, so the value of tau M you will be getting from here is 30 seconds. So you have the value of tau M, you have the value of tau P. Now the total residence time you can calculate is like V divided by V0. So tau, that is V1 by 1 by 60 seconds. So the total time is your, or total residence time is your 60 seconds. So out of this total time, tau can be written as obviously tau P plus tau M plus tau D. This one is 60, that is equals to 20 plus 30 plus tau D. The value of tau D can be calculated as 10 seconds. So now you have all the residence time of all these parameters, that is PFR, CSTR and this dead zone. So now if I write VP, that is, sorry, if I want to write tau P, so what is tau P? So tau p is equals to Vp divided by V naught. But here you are supposed to calculate Vp. So Vp is equals to tau p multiplied with V naught. So volume of plug flow reactor, that is tau p. Tau p is your 20 second into this V naught is 1 meter per minute, 1 meter cube per minute. So that is 1 by 60. If we will do these things, it will be 1 by 3 meter cube. Again, if I want to calculate what is Vm, that is volume of mixed flow reactor for this particular problem, Vm will be equals to what? 30 multiplied with 1 by 60, that is equals to 1 by 2 meter cube per minute. And again, the total volume V total is equals to Vp plus Vm plus Vd. So directly you can calculate that Vt is equals to Vt is 1, that is equals to 1 by 2 plus 1 by 3 plus Vd. The value of Vd will be equals to 1 minus 1 by 2 plus 1 by 3. So once you will calculate these things, Vd will be equals to 1 by 6 meter cube. So you have calculated Vp, Vd and Vm. And now you can go to the option and you can check your option C will be your correct option. Is that clear? So this is how you can use the above equation that I have used for the concentration. So this formula is valid for the pulse tracer input for PFR is connected in CSTR, something like that. Okay, and since when T is greater than tau p, see this one is tau p, the concentration formula you can use, because this is valid for T is greater than tau p and tau p is your 20. So whenever concentration is less than 0, this is tau p, but again this one will be your tau d, right? Because after that time only the tau p will come, something like that. Okay, so this one is very, very important question. With that, I'll end this lecture, and again in the next lecture I'll be doing some different some more questions from the non-ideal reactor only. Okay, thank you.